Good morning, everyone. Till to date, we have seen the single degree freedom system. Then we have went to numerical analysis fully. Then we have done the multi-degree freedom systems also. We have also seen what are the different parameters described in the process. Like for example, um, how we are getting the response spectrum, how we can get pseudo spectral acceleration, what are the different parameters from the response analysis we have also seen. And in case of the multi-degree freedom system, we have also seen how to perform the modal analysis. So it's like more or less gives a comprehensive idea on how we can able to analyze any system like that. Okay, so now we are having the two chapters primarily, or like a two topic we need to cover. One is the continuous system, like bar, beam, frames, like this type of system, and another is the two degree of freedom system. Two degree of freedom system, because that is something the key point of doing any vibration control, because any vibration control mechanism we generally starts from the two degree of freedom system. Okay, so first thing is that once we are talking about the two degree of freedom system, then have like this. So you can say this is mass m1, k1, k2, m2. We can think this like this way, that maybe you have a floor, and in the floor you are having some machine which is revolving with some particular frequency omega, and there always some sort of eccentricity and some type of massing of the lamp away from the center, and this type of things are always occur, and this gives a particular type of vibration to the system. That always happens. If you see any machinery, whatever it is, it creates some vibration. For example, very simple machinery, washing machine. All of you have seen. Once the washing machine is revolving, it gives a vibration. You can feel the type thing is happening. So it has its vibration. If you see also like fridge, all those things, they have a compressor type thing. Sometime we may feel the vibration, but most of the cases we cannot feel the vibration. That's okay. But washing machine type thing, once it is revolving, it's always give vibration. Now industrial machineries also, it is in the manufacturing process or some other applications, it also produces vibration. So in those cases, what happens, like suppose you want to design some floor or some structure, and on top of that you want to put that type of machinery, what will happen? It will create a lot of vibration. So your prime objective is to control that vibration. Okay, how will you do that? There are the two prime way of controlling any vibration like that. First one is the base isolation, and second one is the tune mass damper. Okay, so your objective is to reduce the vibration, and your objective is to reduce the vibration of the main structure by using either of the method. Okay, now if you see, I mentioned at the very beginning that it's a two degree freedom system. Now whatever we are discussing, both the situation can be covered from a two degree freedom system. Just we have to understand what is where. Okay, so first case, if we think that you have a structure like this is mounted on the floor, and you want to reduce the vibration transmission from the machine to floor. So what will happen? You may think that okay, you have your machine here, you will put some type of pad or something like a rubber pad or some stuff, some sort of stuffs, so that your machine is here, and this is actually oscillating, and you are saying that okay, my floor is not going to oscillate. That you are planning. Okay, so in that case, the first question comes into picture: how will you model the full thing? Like this is your floor and this is your machine, So that is your machine, this is your floor, and that is some type of base. It could be a pad or something. So maybe you have also seen, like once we are taking the washing machine or something, we have to take a specific type of arrangement on which we will put that, which is stand or something. So that stand type design is some type of very particular design, that it is not, vibration is not going from that main machine to the floor. Otherwise what will happen, you may be running a washing machine, full apartment can able to listen that yes, somebody is running a washing machine. So that will happen actually eventually. Okay, and it will be more aggravate once you are thinking it for an industrial machine. Then like some industrial machine is working and whole building is shaking, so that could be some problem. Okay, so this is one case. And another case is that you may be having some acceleration on the floor and you want your machine to be isolated. That is happening in case of like some sensitive equipment is placing at some point and you want to control it. Like recently, like with the Gulam, we are doing that problem of the ISROs, that is like camera need to be fixed so that it will not going to vibrate. So that is in the satellite station. So that satellite station is going to oscillate. They have several type of machinery also with it. So they are revolving and that are creating some sort of vibration to the floor. And you need your machine should not have any type of vibration. So you must have some sort of isolation devices in between which will actually able to absorb that full thing, or it will not transfer your vibration from the floor to the structure. Okay, so that case is, so here it is like vibration going from here to here, like machine to floor. So it is machine to floor. And other case, it is like suppose you have a sensitive equipment. So you want it to be such a way that your floor is oscillating, and that is your sensitive equipment, and you want that, so this is has a vibration, so this has a vibration, so this has a vibration. So here the vibration is going from floor to equipment. Also you can see once we are doing some sort of like a simple measurement, I'm not talking about the ISRO type scenario, that is much precise. If you see even a simple lab experiment, suppose you are placing your data acquisition system, or not data acquisition system only, maybe like you are placing your vibrometer or some other devices on top of something, you have to ensure that the foundation of that equipment should not oscillate. Then what will happen? It is oscillating, it is measuring something, so it automatically have that influence of its oscillation. So your result will be perturbed. That will be not a correct result. So in those cases, you can understand the importance of the controlling is very important. Like you want that your vibration should not be transmitted from one system to another system. Okay. So that is, now here two things can be possible. So we have seen that there could be two possibilities may arise. One case, you have some equipment, you want a protection of that equipment from the ground type vibration, and another case, you are having a vibrating machinery and you want your floor should not going to vibrate. Okay, now these two situations can be simultaneously present also. Like for example, if I again go back to that ISRO problem, that like you have a satellite platform type thing, now you have some wheels which are revolving or some machinery which is actually producing the vibration. Okay, so like let's say you have a floor, and on that floor here you have a machine which is actually producing the vibration. Okay, and you have a sensitive equipment here. Okay, which is most of the cases happened, because once you are going some places and all those things, you maybe need to measure it. Like for example, if you take in the vibration lab also, or the metamaterial lab, so there we have a shaker. So once the shaker is driving, it actually creates some vibration. Okay, and if you put some sort of like a laser doubler vibrometer or something to measure that how much vibration is coming, that setup should be vibration free, because this must not have any vibration. Okay, because then your measurement will be perturbed. So what do you do in that case? Like this producing vibration, this produced vibration, and this is maybe the medium which actually transmit the full thing, and this is your sensitive equipment. So you primarily want that your vibration from these, in normal case what happen, you just place it on top of it, and this is also normally placed, this is vibrating, the full floor is vibrating, and your equipment is, and your sensitive equipment is also vibrating. That's a normal scenario. But you have to cut at some stage. Either you want to cut it here or you want to cut it here, so that these transmissions should not be happened. Make sense? Now if you do it here, then you are in this point, that is the source, so you are like mitigating at the source, or else you are mitigating at the object level. Does that make some sense? Okay, you got that problem, that where is the problem and how we can be able to think that. So now first let's try to see what should be the mathematical model for this. Like you have a floor, like this, and you have a machine here. So if we try to see that this problem, what will be its mathematical model? So you have a floor, and we are assuming that floor is going to vibrate. So how should we model the floor? Please tell. Okay, so let's come from the easier one. We have a machine first. Machine is vibrating. Okay, so how should we consider the machine? Sorry? We can consider it as a forcing function. Makes sense. Any other thought? Mass. Now here there is a question or confusion maybe. If you consider the machine as a forcing function, then you are actually neglecting the mass of the machine, because it's a forcing function only. So it just gives a force or maybe varying force, but it do not have any mass into it. So how will you consider that? So in that case, you should consider the machine as a mass. Okay, on the top of mass you can apply a force. Now it serves both the purpose. You have your mass of the system and you are also applying the force, so that you can able to model that, okay, variation of the things. Okay, good. Now it is supported on the floor, so some support. How we can able to model a support? Spring and dashpot. Perfect. Because spring will actually do what? Spring will provide the stiffness, and damping will provide some sort of dissipation from that. Okay, now next thing is the floor. How should we model the floor? List mass, spring and damping. Okay, before we draw it, now let's try to think the proposal that we should model the floor as a spring, mass and damper. Okay, now suppose, now let's think, if it is not instead of a floor, if it is the ground, then what should we do? Then we should maybe just model it as a fixed. Okay, but now here why are we modeling it as like a spring mass? or spring mass dashpot. Why? Because we try to measure the vibration coming on the floor. If we do not need to measure the vibration coming on the floor, we don't bother. We may just freeze the degree of freedom. And freezing the degree of freedom means we are putting some boundary condition on top of it. Did you get that point? Did you understanding that how the real life problem can be modeled in the forms of structural dynamics problem? Because this is a real life problem we took. That like some machine is there on the floor, and now we are trying to think that okay, how it is actually we can able to model that full thing. Okay, make sense? Good. So here we need to then model it as a. Now tell me that I completely agree. So this is representation of my machine. This is representation of my floor. Okay, very good. This stiffness spring set is representation of the base. Okay, base of the or the mounting or the mounts, base or mounts. What is this? Please. Column, okay. Columns and slab. Exactly. But just one point, if you think columns will be in the horizontal direction. So if you are thinking that this vibration is creating the horizontal direction, then his point is very correct that it will be like a column stiffness. But if it is producing in the vertical direction, then you have to consider the flexibility of the beam and slab. Agreed? So you have to actually start feeling the problem, that what you are actually solving. Get that point? So if the machine is giving a horizontal motion, it could possible. Like for example, if you drive the shaker in the horizontal mode, like where the shaking will be happening in this direction, then it will produce a horizontal motion. So in that case, you have to model the that spring and damper will be the stiffness of the columns. Absolutely all right. But if you place the shaker like this way, vertical manner, then it will be the floor stiffness will actually act in that case. Feel that problem properly? Can able to visualize the full scenario, what is happening? Perfect, everybody? Anybody has any confusion? Perfect, good. So we understood for horizontal, that is mostly the columns stiffness, and for vertical it will be slab or floor. Slab or sorry. This will be slab or our beams. So that will be the stiffness coming from these two. Agreed, all of you. And that is only required once you want to measure that how much force is coming on the floor. Otherwise, you don't bother. Otherwise, you can just make it as a like a directly slab type thing. There also you can able to calculate, like for example, if it is a foundation on the ground floor you are placing it. In that case, you may also need to find out how much force is coming on the ground. Okay, but in that case you don't need to model the floor as a spring mass system. You just can only model it as a fixed support, and you can calculate still how much force is transmitting on that. That possibility is still there. Okay, because suppose if you are modeling some sort of like a DG set or something, that also like a quite rigorous designing, and nobody put the DG set or something on the very top. No, they just put it on the ground because that's a very massive structure. So once you are doing that, then you are actually designing it for the ground, and you are not considering that at all that this is also going to vibrate. This you are assuming just like a full fixed, but still for designing you need to estimate the force. and that force you can able to calculate that how much force is coming from k into x, or maybe k into x plus c into x dot. Okay, that way you can able to get how much force is coming on that. Agreed? There are two types of damping generally present in this type. One is that air, like a viscous damping, or whatever the medium it is, like it may not be in the air, it may be something different. And second one is the material damping. Like suppose if you take a rubber or if you take a steel, if you try to put the shear, you will see that both the thing does not have the similar type of damping, because that also depends on interconnection between the two layers of the medium, that how they are actually interacting. If there is some deformation, how much energy is getting dissipated from that. Okay, so generally the two types of damping are always present in that. Okay, one is the material damping and another is the viscous damping type thing. We will see that in much detail once we do the continuous structure. So there we will explicitly write, means in the equation of motion you will see that two terms separately. Okay, so this we establish the equation. Okay, now what is our objective? By the way, we do all those things, nice, we set up. So maybe we can just think that this is u1, this is u2, and this is my k1, this is c1, this is k2, this is c2. Okay, equation of motion should not be any big deal. We can just directly write m1 m2, obviously put it m1, this is m2, m1 m2 with u1 double dot u2 double dot plus, just write q1 okay. Can I write the equation of motion like that? Like first I just put mass matrix m1 m2 with u1 and u2, means with u1 double dot and u2 double dot as in the sequence. Then I put like k1 minus k1 minus k1 k1, and then as the third degree of freedom is fixed, so definitely k2 cannot be written completely, so that is k2, and then minus k2 minus k2 k2 will be cancelled out. Okay, and accordingly the stiffness matrix is also written. Okay, and that should be equal to f and 0, because force is only applied in the first degree of freedom, not in other degree of freedom. Okay, any doubt up to that? Okay, now in that case, what is my objective? What I am looking for? Huh? Response, yes, but you so my target is to reduce the vibration on the floor. Agreed? So which one I am trying to reducing? u2 or u2 double dot, automatically it will be happening. So u or u2 or u2 double dot or u2 single dot, we try to reduce. Okay, that is my target to do that. Okay, good. Okay, so before we go there, let's just try to write another way of doing that. Okay, before we go and start solving this. Now next case, you may be having, okay, so suppose if you, okay, so you can also do another way. Okay, no problem. You can just go ahead first with that. But we can do it later. Okay, so here, as very nicely mentioned, that our target is to reduce this thing. We try to reduce this U2. Okay, how can we solve it? Now here there could be two things. It will first try to identify, is the problem is a free vibration problem, forced vibration problem? Forced vibration problem. Okay, so then where should we going to focus? Because if it is a forced vibration, then the response will be of two type. That is, means the response has the two type of component. Basically, you can say one is the transient part and another is the steady state part. So which portion of the response should we focus? Transient or steady? Steady. Good. There is also some point we need to also understand. Definitely we will focus on the steady state, no doubt on that. But some point is where, like for example, once you start the machine, then the machine will undergo through the transient part and then reach to the steady state. Because it's never possible that the system will directly go to the steady state. That's not possible. System will take some time or it will undergo some cycles to reach to the steady state. So we should keep in our mind that it will undergo through that process. Okay, and in some cases often the requirement could be quite changed. For example, again if I talked about the ISRO problem one, that suppose you are placing it with the launching vehicle. So there could be two type of scenarios. Maybe it is launched, so that time it subjected to a very huge thrust, and then your vibration will be like a normal level of vibration. So that different scenarios can also be very much possible. So once you are going to design any sort of isolated system or something, you have to have a very clear understanding of what you are going to oscillate. I mean, what you are going to isolate actually. Okay. So that is, but ultimately your target is to reduce the U2. And also once you are thinking that, okay, your system is subjected to what type of motions, because if we are talking about the steady state only, means forgetting the transient part, if we are just talking about the steady state part, then also the question comes that what type of frequencies or what type of excitation we are assuming there. Okay, so now let's try to think what are the possibilities. Suppose if it is a machine, like let's say washing machine, which is very commonly known to all of us mostly. So how the washing machine functions? Anybody? It has a drum, it just revolves, and well, I don't know also the internal mechanism how it is doing, but I think that is also not required. It is like a drum is revolving primarily. Okay, so it's a revolving mass. Now once it is revolving, we maybe have seen there are some speed what we can able to control. So that is associated with the revolution of the drum. Sometime maybe we are using it as a dryer, like we just spin it so that it will get dried, and sometime for washing, for different types of washings are also possible. Some programs are there, P1, P2, P3 was written. So they are basically controlling the speed of the revolution. Now once the revolution speed is get controlled, that means what? We are actually controlling in the viewpoint of the structural dynamics. Frequency, exactly. Forcing frequency. Forcing frequency we are controlling, because revolution is happening. So that is directly proportional with the frequency. If it is high speed, that means high frequency. Low speed, low frequency. Very clearly, it's very clearly correlated. Okay, and also, and then where is the forcing amplitude? How many clothes you have given? That is the load, because that load is moving. You have put so many clothes, It's a full, so it's revolving with a full mass. So that amount of mass is get increased. Okay. Now if you run it in the small amount of cloth, mass will be get reduced. So I think you get a sense that exactly from where the amplitude of the motion is coming and from where the frequency of excitation is coming into place. Make sense? Got that idea? Okay, good. So now once you are designing it, now you have an idea that okay, my P1 button gives this much of speed, P2 button gives this much of speed, P3 button gives this much of speed. Obviously the user don't know it, but those who are manufacturer, they definitely know that thing. But otherwise they cannot able to manufacture it. They set the drum to rotate in that particular rotational velocity. Okay, so they know that how much rotational velocity you are getting, what is the RPM of that. Okay, so these are actually a harmonic vibration because these are giving a particular frequencies. You cannot run, like suppose once you have run it for a particular P1, maybe the P1 program you set, so that associated with let's say 30 RPM. Okay, means 30 revolutions it will have in a 1 minute. Okay, so whatever hertz, whatever radian per second you can calculate. I am not going into that. So that is a specific and you cannot change it. Let's say your one washing cycle is let's say 1.5 hours. So you cannot able to change it in 1.5 hour time. So maybe first few cycles, maybe 1 or 2 seconds, it undergoes to the transient and then rest of 1.5 hour it is running in the steady state motion. So what will be your objective? To control the transient or control the steady? Definitely control the steady because it will be there for the so long time. There is no doubt on that, and I think everybody can able to correlate also. Means mostly I hope everybody used the washing machine at least sometime in their lifetime. So yeah. So by this way we can able to see that how it is actually happening. Okay, so that point it is particular frequency. So let's say your P1 program is correspond to a particular frequency, let's say like 300 RPM. Then P2 maybe is corresponding to 40 RPM. Then maybe P3 is defined with that like let's say 60 RPM. So like this way your speeds are different. Okay, sometimes you may see it said for the delicate cloth, these, that, so many things were there. So these are all having a different types of RPM primarily. And if you are running it in the dryer mode, then dryer is also having particular frequencies. So these are there. Okay, so you have to then, so your isolator now basically should able to reduce the vibration for those frequencies primarily. It must not able to let the vibration goes for these frequencies. The strategy is clear. I hope you get that idea. Now, what should be the strategy of designing any isolator? Okay. Now, this is the case once we are talking about some machine in there. Now, this similar setup can be also seen, for example, you know, wind turbine tower. Maybe not that common like washing machine, obviously. Wind turbine tower, maybe a lot of people have never seen. How many of you have seen a real wind turbine tower? You have seen, great, good. So 2 people have seen the real wind turbine tower. Okay, so obviously I can understood that. So these are like a very tall tower, obviously. Like for example, if you see like a 5 megawatt wind turbine tower of Vestas or Siemens, that is somewhat 90 meter tall, and the blades are of 60 meter. Can you imagine? 60 meter means it's a 20-storied building. That blades are, and the total tower is 90 meter. That means around 30-storied building. And you are and there that full rotor system is placed on the top of that. So like it's, some people are very nicely called it like you are designing a lamppost, assuming that you are putting a washing machine on top of the lamppost. So this much level of vibration is coming on the wind turbine tower, because the full DG set is there, means the full like a generator unit is there, and it is subjected to a big amount of wind because it's a 60-meter blade. So like the full diameter is 120 meter. It's now revolving, so you can understand that how much wind thrust it is subjected to. And it is also in some cases offshore or maybe some cases onshore. Fluctuation of the weather and all those things is extremely very high. Because wind turbine tower, you are not designing in some sort of like places where the wind velocity is less. That's not the scenario. And one of the other MTech student is working on that, like he was from army. So in the Kargil, they want to install the wind turbine tower. And those who have the idea about the Kargil and all those places, they can understand the severity of the weather. These are not at all like a normal terrain even. So how you are going to put those things there? Like there is a so much huge wind thrust, because you should put the place in the place where there is a wind. You cannot just put it in the Delhi there is no wind almost, or maybe rarely wind is coming, so your full investment is gone. Okay, so so in those cases your excitation spectrum is not as defined like this. You are not having a particular peaks that okay these are coming at these peaks. Rather you are dealing with a wide band of spectrum where the loads are coming in a spectrum. Okay, so maybe that is following some Devonport spectrum or maybe Keimer spectrum. This type of spectrums are going to be used for that. Okay, so these are for the wind. If you think now, if you think for an earthquake, that will also not a particular spectrum, that can also vary. So if you are talking about a real life disaster point of view, your spectrum will never be a sinusoidal spectrum. You will have some type of random spectrum, or some type of like a spectrum is like a defined spectrum, or maybe a white noise or some type of things will be happening. Or if you are doing it this type of scenario, you will have like for a specific machine, you maybe have some specific frequencies. Okay, I think the idea is getting quite clear to all of you. Okay, perfect. So now if you try to see that how we can able to solve that problem, so whatever is that, so it may be wide band or it may be narrow band, it may have particular frequencies, or so at the end point we can say that frequency or the forcing function can be of any type. Okay, but the good point is that we have already seen in our numerical analysis course, I mean the numerical analysis portion, that whatever the forcing function, it hardly matters. We have the Fourier transform. We can able to encounter anything literally, so we don't need to be worried, and we can able to solve the full problem in the frequency domain. And using the Fourier transform, we can transform the excitation and we can again get the response as like a single degree freedom, as like a harmonic excitations. Agreed, all of you? Yeah. So we will use primarily that technique, and we will try to solve it for a harmonic excitations, and because we have that Fourier transform. So if I have this one, so now what I will do, so I primarily have this matrix M1 M2 U1 double dot U2 double dot plus C1 C2 minus okay. So if I just try to write it, so if f equal to f into e to the power of I omega watt t, which is nothing but a harmonic excitation, so how can I write the u? U1 should be equal to capital U1 into Come on. E to the power I omega bar t. Simple, because we are considering the steady state part. We are not considering the transient part. Here is that big difference. Once we are just writing like this way, that means we are neglecting the transient part. We are not solving it for the transient part. So never try to match this result with a numerical result, because if you do a numerical analysis, like suppose you have the initial condition and all those things, you implement the Runge-Kutta method or maybe the Runge-Kutta method or something, you will get transient plus steady both. But if you just assume like this and solve it, you will get only steady. So do not try to match the two results. Obviously your steady state response amplitude will be remain same. You should get the same response in the in terms of the response parameters. Like for example, amplitude will be remain same, frequency output will be remain same, but do not expect that they will exactly match. If you just plot the two graphs, they are necessarily not that to match, because there is a transient part and then from transient part it will come to the steady part. But here you are just only looking the steady part. Okay, but this solution is much more preferred, this steady part, because transient part solution is not invertible. Not invertible means from that response you cannot directly go back and calculate the parameters, but it's a design problem, so we need to invert the problem. We need to design that what type of stiffness value, what type of damping value we need to place. Okay, so whatever. So if we have that, I can able to write it minus omega square m1 plus I omega bar c1 plus k1 minus I omega bar c1 minus k1 minus I omega bar c1 minus k1 minus omega bar square m1 plus m2 plus I omega bar c1 plus c2 plus k1 plus k2 with u1 u2 should gives you f and 0. Okay, so if you try to just I put all the stuffs there and add them up. Okay, everybody all right? Anybody has any confusion? Okay, no issue. So now let's say my target is what? Reduce what? U2. I would like to reduce the U2. So first I have to calculate what is the value of U2 then. Agreed? Because okay, so how can we calculate the value of U2? Simple way you can do it. If I just take the last row of the equation, what can I get? I omega bar c1 minus k1, or maybe I will just do like this way, u1 equal to, or maybe plus omega bar square m2 plus I omega bar c1 c2 plus k1 k2 into u2, that is equal to 0. Okay, so what is my u1? So my u1 will be this full thing plus I omega bar c1 plus c2 plus k1 plus k2 divided by I omega bar c1 plus k1. Okay, that is my u1 in terms of u2. Perfect. Good. Yes. Good. Okay, anybody can able to answer that? How can we able to assume that all the masses are also going to oscillate in the same frequency? Anybody? Very good question. It seems like other people also don't know that. Very good. It is a steady vibration. Steady vibration means, if you remember the way we defined it, like you came from home and now you are in hostel. So you had your previous state of vibration mode, that is maybe your natural frequency. In hostel life, you are start finding your frequency is, means the hostel's frequency is something excitation frequency. So after certain time, you will start exciting with the hostels. You will not have your own properties. So that is the steady state vibration, and their full system will oscillate in the excitation frequency. So that actually drives it. So that the transient portion happens once it is going from its original frequency to the steady frequency, which is the excitation frequency. Makes sense? So therefore, your all the masses are oscillating in that excitation frequency. Come on, if you have some queries, some confusion, please feel free to ask. Very good, thank you. Okay, so U1 in terms of U2, we can able to write. Agreed, all of you? Perfect. Now, simple. First equation will give me what? Okay. So now if I just substitute with that one, so that term will gives you the displacement. And what will be your objective? So if I just say that this is some type of, maybe just say that chi times chi as a function of omega bar. Why I'm saying it's a function of omega bar? Because if you start checking what are the terms, M1 is a constant for the particular system, because that representing your machine. So machine mass is constant. Perfect. Then floor mass is M2. Okay. So M1, C1 is that mount, Q1 is that also the mount stiffness, M2 is the mass of the floor, C1, C2. So these all those things are known. Which is the prime varying thing? That is omega bar. Here omega bar is varying, that means you are changing the excitation and you try to see that for different excitation frequency how your structure is going to oscillate. Okay, makes sense? Is no doubt, no confusion on that? Yes. So if you see, M1 is representing the mass of the machine, means whatever with the subscript 1, that is representing the machine and its mount, and then whatever with the subscript 2, that is mostly for the floor, like the stiffness, mass, damping of the floor. So these are primarily the constant. Okay. Now I am not talking here the designing of the mount. If I am talking the designing of the mount, then K1 and C1 I have to calculate. But if I just think that some mount is fixed and you just placed on top of that mount, in that case your K1 and C1 are already known to you. Okay. And we try to see that how the response are getting changed for different excitation frequency. So what is the different excitation frequency here? That is omega bar. So we will And if I just think that full thing is something like chi times omega, I mean the chi of omega bar, then I can say that u2 will be f divided by chi of omega bar, or chi of omega bar. Okay. Now, what is the important point? That we try to reduce u2. That means maximization of the chi of omega bar is my target. Agreed, all of you? That we try to maximize the chi of omega bar so that we can able to get the solution. Whatever the big value of the chi of omega bar will be, your displacement will be less. Okay, so you can plot that function also, and you can try to see that how the function is actually looking like. So obviously, once you are plotting that function, your x-axis should be with omega bar, and you will plot that g of omega bar function, and you will try to see that how the responses are. Okay, or you can write it in the different way also. Means you can say that this is 1 by this, so that you will get it. That is actually better way to do it. So that you can say that, so the reduction of the chi of omega bar will gives you the solution. Okay, means if we just assume that this full thing is 1 by omega, 1 by chi omega bar. Okay, because that is up to you that how you are assuming it. Okay, so that gives much better sense to do, because if is a constant term, like let's say 1 you have given, so you try to see that how it is changing. So this problem is clear. Now we may have another set of ways we can do that. So this is the way of doing the base isolation. Okay, oh yeah, so before we go there, now, so these will give some sort of graph like this type of way. You will able to see some graphs will come. If you plot that, you will able to see that. Yeah, so this graph is actually for, like, once you are having all the values, you will get this graph. But once you are designing it, then your objective is to find out the value of C1 and K1. Because if you are designing it, that okay, I want to design a mount, you want to design a support, then you are actually looking for that one. So in that case, how are you going to do that? There is a several technique of doing that. First, you have to identify what type of spectrums you are dealing with. Like suppose if you are trying to find a mount for the railway vibration, it will be different. If you try to get a mount for the ISRO type problem for the for the space station, that will be different. If you want to get a mount for the submarine DRDO type problem, that will be also different. Or if you want to have a base isolator for your building, that will be different. Or if you want to have a base isolator for wind turbine tower, that will be different, because all the problems will have encountering the different types of the response spectrum basically. So that you have to consider, and the requirement may vary. Okay, so that we will see in the later classes that how we can able to incorporate that. And there also some portion from the random vibration will also comes into picture, because that is not directly possible to do by the normal vibration problem, like a designing of that isolator, because you have to perform some optimization analysis. Based on that, the standard deviation of the response is getting reduced. And obviously we are not talking here any statistical quantities related to the structural dynamics. This is like structural dynamics itself, we are looking it as a deterministic process, not as a stochastic process. So that is like a next version of the structural dynamics, which is a random vibration. So there we are talking more about the randomness of the process. So there are like a two types of randomness we considered. One like uncertainty associated with the excitations, and uncertainty associated with the model itself. So that we discussed there. So that is not a part of this course also, because that is like a significant jump. That is not at all like a small thing, because it is not a deterministic, means you can understood that the domain is completely getting changed. Like from the deterministic side, you are going to stochastic side, and instead of a direct parameter, you are now going to use a statistical parameter, like a response itself is so many points. Now you have started talking that okay, the mean of the response, standard deviation of the response. So you can understand that the language itself will get changed in that case. So we will definitely not going to do that in this course. So otherwise it will become too much, too ambitious, and we should not do that. Okay, but I just try to tell that for doing this type of thing, you have to basically go and check the random vibration point of view, not directly from the deterministic approach. Okay, good. And we also work on that thing, like several isolated designing and all those things we do in past, so using the random vibration. Obviously that is not possible with the normal vibration. So there is some sort of like H2 optimization technique, H infinity optimization technique we can actually study. That is not from the stochastic point of view. That is from the deterministic point of view. So that we will do in the next class. We will do that H infinity one, but not the H2, because H2 is like a second norm, and that is nothing but the standard deviation. And we are not doing the standard deviation and all those things in this course, so we will not going to do that. Okay, means that is itself a full subject, full course itself. Yes, please.
So, we are going to have a super code. It's natural frequency of the sites is not the band what we are considering the forcing vibration. Suppose my forcing vibration is 1 hertz to 2 hertz. I can go for my base frequency more than 2 hertz or something. It is not possible that like
Yeah, deterministically it is possible, because first generally we thought from the deterministic point. Obviously, because we cannot directly thought from a stochastic process. The stochastic process is always complicated. So suppose if you say like if you ask me to design it for like a 1 to 2 hertz, I will say maybe try to design it for 1.2 hertz frequency. It will do a good job for 1 to 2 hertz. Why 1.2 hertz? Because 1.2 hertz is generally, once you are having some system, you maybe have seen the DAF diagram, dynamic amplification diagram, that is the increase, like once the peak is increasing, that is more close to 1 from the left hand side, means once the frequency is less, that is more close, but once it is getting higher, that portion is like a longer side. So if you put it around 1.2 to 1.25, then more or less able to cover up your 1 to 2 requirement. But if you put it around like 1.7 or 1.8, then it will be shifted from 1.5 to 3 maybe. So that type of things generally will happen, and there are also several ways of doing that. Means what I just showed, that is a very basic way of doing the vibration control. Now you may be able to put the resonance in the vibration control in the base isolation as well. So that particular frequency will be automatically entrapted. Yeah, so that like a trade loads are coming like this. So that has some interval, because why these intervals are coming? Because of the placement of the wheels, and once it's moving in a particular speed, then these wheels are coming after certain times. So that gives a particular excitation frequencies. So now what we actually thought that okay, this is my excitation, so that maybe the rail on top the wheels are moving. Rail means we called it that patri, this on which the rail is moving. So that is the rail, because that nomenclature need to be very clear, because a lot of people are using it in the different sense. So the rail means that rail line. Okay, then we are having like here the slippers and all those things are coming, but in between there is a pad. and we primarily worked on that pad. So that pad we normally like think it like as a spring and mass damper, but we just say okay, don't go for it like that way. And then the slipper is also sitting like this on the sub base something, so this is also going to oscillate, that is also going to oscillate. So the similar problem, you see, like same problem can be used in the different cases and the different manner, but the problem is even same. So here what we do, we instead of having this portion like this only, we put it here another mass, so that these can also able to dissipate some amount of energy. So this is mass 1, this is mass 2. Mass 1 is nothing but the mass of the rail which is getting excited, and mass 2 is another portion which is getting oscillated, and then we have a spring mass full devices are there, and this is the slipper mass, okay, is coming, and then we are having like a base subgrade modulus and all those things. So that can able to entrap your motion. Now suppose if you are having this rail speed at certain like certain level of speeds are there, some variation. Now people are going from normal rail line, they try to move the high speed train. So for those things, what is happening? Once they try to go for the high speed train, they are not at all in changing the infrastructure fully. But once they try to do that, obviously it will create more vibration. How are it going to sustain? Like the one problem is that like the lines were designed for 160 km/h. Now they try to make it around 250. It is easy to say just 160 to 250, but that's not easy to do it in reality. Because you see in the foreign perspective, the rail bogies itself getting changed because they are not driving the steel bogies, because steel bogies is much more weighty. They have a much mass. The axle load is very high. But in those cases they are using the aluminum bogies, but most of the cases they did not change it. They just driving the steel bogies with that velocity, so it is like giving huge load. And some of the cases the lines are not that good, so that's maybe increasing the accident and all those things. So these are the issues happening. So in those cases, these are some sort of cases very good solutions, because what happen, you are interrupting these type of motions automatically into it, because that giving some oscillations and it dissipates the energy. So this happens. Okay, so this way that some of the different cases people can design. So design is like it's a full-fledged thing that people can do various style and do the various ways. So that is how we are talking about the base isolation point of view. Now if you are going for the tune mass damper point of view, which is another aspect of it, that is like suppose you have your system, then you have your so suppose this is your machine, or now it can be rail, wind turbine, whatever. We have seen that all the systems are primarily falling into that 2 degree of freedom system. No matter what is it is, you can able to convert it into that. Then this is your floor, slipper, whatever, and that is like this. So now you say that okay, I do not want to put any special type of thing here. I just put a mount, simple, normal, but I don't care that much how what is happening. Rather, what I will do, I will put another mass spring system on top of that, so that it can able to sacrifice itself once there is the vibration. Means instead of having the oscillation in the main machine, actually sorry, I put it in a wrong place. Sorry, that should be put here. So that's the tune mass damper. So what do? You just placed another tune mass damper on the system in such a manner that whatever the mount is there, I don't bother that much. I just put another tune mass damper. So what happens? Once it is oscillating too much, it will take all the vibrations. It will not let the floor vibrate that much. Okay. And also, I would like to say that my full PhD research, and also for what like people little bit know me, that is the metamaterial topic. The fundamental key aspect of the metamaterial is from the tune mass damper. We try to design this type of tune mass damper inside the material system, so that the material system itself can able to do that vibration control instead of going for any other type of special level, like that pad and all those things what we are designing and all those. So they're all having that impregnated resonator, so that can able to oscillate, insulate the vibration by itself without going to some other places. So that's like a complete different research domain itself fully. So this is the scenario happening once people are designing like that. Okay, so they can able to place some type of resonators on the floor, so that the motion directly go to that resonator, not on the floor. Floor will be keep calm and quiet. This is something similar to the fuse. Like for example, in electrical circuits, you have seen the fuses that once the more flow is going, fuse will burst. Here also the similar type of things are happening, that they are putting some fuse and they will be blown. And so this is the fuse. Once there is some more vibrations happens, or some of the cases, they actually absorb the full vibration. Now whether it is going to fail or not, that depends on the designing of it, but it will take the more vibration, it will just start oscillating. But this type of situations are very good for specific frequencies. Once you are having the different frequencies or like a broadband excitation, then designing like a tune mass damper is a big challenge. So there are like several stuffs we have done, like non-linearity, these, that, like it's full research domain. Actually, like instead of this a linear spring, maybe people put it as a non-linear spring. Instead of a linear damper, people put it as a non-linear damper. Several things people did. Okay, so that's the way this thing people means some of the cases we do. So in the next one, maybe we will try to see like one problem on the vibration control, that how we can able to design, not design, at least like find out how the responses are coming, how much energy is going. Like suppose if you put a tune mass damper, how much energy is going to the tune mass damper and how much energy is still remaining to the system. So these all those things we will try to see. Yeah, tune mass damper is also used in another case, that is like once like you are having like your machine, on top of machine also people can put it, then directly the machine will not going to oscillate, that is directly oscillating the, so the base itself will be very, very quiet. So yeah, so by this way, yeah, so so these are some of the things we will see in the next class also, and we can go ahead from that. Okay, so thank you very much.